Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon. Welcome to the seminar. We are very delighted to have Professor Jennifer Widom here from Stanford University. Many of you know her already. She did her PhD from Cornell in '87, worked at IBM Almaden, and then joined Stanford.
93.
93. Okay. And so she's extremely well known and extremely accomplished in our field. And her background was actually more interesting than most database people's background is. She started off in music, and then programming languages, and then databases. So you see how important databases are. This is one index.
Well, I've stuck with it for a long time
yes,
now.
Yes. She has been winner of numerous awards. Specifically, database community gives an award which is Test of Time Award, which is look back 10 years and say whose paper had a great impact. And she had won it actually multiple times, which is saying a lot. Very few people can claim that. She also had, much before XML became fashionable, she worked on semi-structured data and had a project on lore. She has a very well-known textbook that some of you may have even used. So I don't think I need to introduce her anymore. The last thing I would say is she is a member of the National Academy of Engineering. And with that, I'm going to have her speak on Stanford Data Streams project, which is a project they just completed, and we're going to hear everything about that.
Thank you. Wow, what an introduction. First question, how do we want to plan the timing? I have a talk and then I have a demo. And the demo is crucial, I think, and that's sort of roughly 10 to 15 minutes. So
I guess if we wrap up by, if we plan to wrap up everything by 2:45.
Easily.
Yeah. And
depending on your audience, of course. But
just about a few minutes above 1 hour.
okay. That'll work out just fine, I think. And let me say that I love to take questions during the talk, so please feel free. I can adjust what I talk about according to your questions, and I would much rather know that you're listening and have questions than have you all sit there quietly and blankly. So do please go ahead and ask questions. So I am going to talk about the work that we've been doing at Stanford in the area of data streams. It is a project that's been going on there for quite some time and in fact is ramping down at this point. So you're going to in some sense see a finished project, not in the sense that there isn't more work to do, in the sense that the students who started this when they came to Stanford are now graduating and the new students want to do different things. So there's lots more to do, but I'm going to tell you what we've been working on for the last 5 years or so in this area, and I will finish by giving you a demo of our system, which you can all also use over the web, and you can also download the code for the system. So first, let me give you my surefire formula for a database research project. I think some of you have probably seen this couple of slides before in the context of other projects, but here it is if you ever want to start a database research project. Just look at a typical database system, pick one of the many fundamental assumptions that underlie the way database systems work, and then just drop that assumption and see what happens. What really happens is everything unravels. You have to reconsider typically a large number of different aspects of the way data management works, the way query processing works. Now, from my point of view, that has some great attributes. First of all, it produces many PhD theses, because once the whole system unravels, you have to put it back together, and its many different pieces can constitute many different significant pieces of research for students. The other thing is that when everything unravels and you want to build a system, you have to put the system back together, and typically we've been doing that from scratch so far. So I've followed the formula a few times. Tell you what assumptions we've looked at dropping. As Suraj had mentioned, we worked even before XML existed actually in the area of semi-structured data, and in that case the assumption we were dropping was a very simple one. It just says when you have a database you have to declare your schema and then you have to load your data, and your schema isn't going to change much, might change a little bit. So that was the simple assumption we dropped that made everything fall apart, and we worked for years trying to put that back together. A project that we're just launching now, which is called Trio, and I can explain offline why if people are interested, drops another simple assumption that underlies the way database systems are built, which is the assumption that when you have a bunch of data in a database, you have all your data, it's complete, and the data itself is an accurate representation. You don't sort of care how it's changed over time. So that's a project we're just launching, and I'll maybe come back in 4 or 5 years and tell you how that turned out and show you a demo. For now, I'm going to talk about the STREAM project. And STREAM, by the way, stands for Stanford Stream Data Manager. If you can read it down in the lower left corner how we map that. So the STREAM project also drops a pretty basic assumption about databases, which is how you create and query your data. So the typical assumption once you've created your schema is that you then load a bunch of data, you index the data, and then you run queries over it. You run a query over a snapshot of the data, that query is done, then you run another query, and that one is done. Okay? So when we drop that assumption, what we're looking at instead of traditional stored data sets are continuous data streams. But that's really only half the picture. And a lot of people talk about data stream projects and data stream processing. But data streams, to me, aren't that interesting unless you couple with them a new query model. And that query model is continuous queries. And that's at least half of the issue, in my opinion. So the point being that when you have data streams, which are constantly coming into the system, it really makes very little sense to issue a query, get an answer, and then later issue another one. What really makes sense is to register a query with the system. The query sits there, and then as the data streams in, the answer streams out, or the answer is modified over time. So that's the other difference. So let's talk a little bit about data streams. We define a data stream to be any sort of continuous stream of data coming into the system. Typically, we expect them to go on for a very long amount of time, maybe unbounded amount of time. They can be very rapid, though they don't have to be. They can change over time in both their arrival rates and the data that comes along in the stream. So that's what we define as a data stream as opposed to a typical relation sitting in a database. And I've listed here a number of applications that generate data streams, and I think it should be clear to you. There's monitoring applications. Most of these are monitoring, but capturing web logs, capturing processes all fall into that category. So that's the setup. What we were interested in doing when we started out was building a general purpose system that looks like a traditional database, except it makes this change in assumption where the data is coming in as streams and the queries are continuous rather than one time. And we dubbed that a data stream management system, or DSMS, instead of DBMS. So at the highest level, let me just point out a couple of differences between a DBMS and a DSMS. First of all, as I've already said, a database system generally manages persistent collections of data, for example, relations, whereas a data stream system is focusing on these transient data streams, although every application I know of, I think, also has some persistent data going along with the data streams. That's typical. And the other half, again, is the query half, where in a typical database system, you have a one-time query. In other words, you ask a query, you get an answer, and you're done. Whereas in the data stream system, you have a continuous query. So from the user point of view, those are the fundamental differences. If you look under the hood at a high level, in a database system, you're typically looking at random access to the data. Okay? In a data stream system, you're talking about sequential access because you typically want to process the data as it streams in. Now, you may also take that data stream, write it off to disk, and do some typical random access patterns over the data once it's there. But we've been focusing on the what do you do as the data comes into the system, and then you really don't have a choice about the order in which you process it. And in terms of query processing, in a database system, there's, as we all know, the typical mode of query optimization where you get a query, you know how the data is laid out, you know what indexes there are, and you think about how you want to best execute that query based on the layout of the data and the statistics over the data. In a data stream system, it's a little more complicated. You've got a continuous query sitting in the system, and you may have a plan for how you're executing that query, but you really don't know what's coming in terms of the data. So it's not like you have any guaranteed statistics about the data when you figure out how you're going to process the query. Okay? So those are the highest level differences. Here's a picture of a data stream system, extremely abstract, but just so we all have the same idea in our mind. So here we have our DSMS, and we have, I've just labeled 3 components here. One of them is, as I said, there's very often stored data in an application. So this could be a typical relational database or other type of database. You may want to write your streams off to an archive. So by the way, forgive me if I sometimes say read a stream element and throw it away. You don't really throw it away. You typically might write it off somewhere and query it later, but I'm not going to talk about that much. And then the one important thing is that a lot of applications of data stream systems need to process data on the fly very quickly and keep some amount of state to do the processing. And we'll see examples of that. So I'm calling here this scratch store the state that's kept for the very online pseudo real-time processing of the streams as they come in. And here, of course, are the streams coming in. So what happens is users will come along and register queries, maybe even before any streams start. And then as the streams come in, results are going to be streamed to all the continuous queries that are registered. You don't have to have a stream model for query results. You can also have, say, results of a query, of a continuous query, be a table, and then just have that table updated as data elements stream in. So very simplified, but we'll talk about some of these components in more detail. Let me just map this quickly to network monitoring, and again, fairly abstract, but in network monitoring, these streamed elements might be, for example, measurements on how the network is behaving, packet traces, for example. There may be lookup tables associated with routing, for example. And then users will be registering monitoring queries for a couple of purposes. One of them might be for intrusion detection, looking for patterns that are indicating some kind of problem on the network. And you can also use the same setup just for performance metrics, so people can have a dashboard and look at how their network is behaving. Okay? So here's my quick defensive slide. I don't want to spend a lot of time on this, but I often get these kinds of questions. I'd be happy to talk at length outside the talk about this particular slide. This is my slide explaining why you can't solve all the problems I've just described using a conventional database. Someone might say, oh man, just create your tables, your streams turn into inserts into the relations, just set a trigger or create a materialized view for your continuous queries and you're done. So there are a few reasons that this doesn't work. Here they are. One of them has to do with just the mode of getting data into the system. So the typical mode in a database system is that you're going to batch your inserts. You're going to get a big batch. You're going to load them. Later you get another big batch and you load them. If you try to do, say, a JDBC call for every tuple on a data stream, you're out of luck. Now, I don't think that's an insurmountable problem. I don't think that's the biggest problem, actually. I think this problem can be gotten around. It's not the typical way, but you could probably make it work. But there's some other problems. One of them is that typical triggers have fairly simple conditions that they're triggering on. Or if the triggers have very complex conditions, they're not handled very efficiently. And if you're thinking about using a materialized view, actually you'll see examples coming up where you want to be a little more expressive. You want to talk about in streams frequently about sliding windows, for example. And that would be very difficult to talk about in a materialized view. Although you could do it in contorted ways, it's not very natural. You'll also see that some of the work we've been doing has to do with giving approximate answers to continuous queries when you have bursts in the streams or overload. And that's something that's just not naturally handled whatsoever in these alternate approaches. And current systems aren't very scalable in terms of triggers. Views don't provide streamed results. So there's a number of reasons it's not a very good fit. And I'll mention at the very end some work that's been done on benchmarking stream systems compared to using a conventional approach. So, any comments so far? Anybody want to get defensive on my defensive slide or offensive? No. Okay, good. Let me talk a little bit about our system, what we've built. It follows what I've said so far. We have in the system data streams and we have stored relations. We have a declarative language, looks a lot like SQL. I'll be showing it to you in a bit, for registering continuous queries. So that's from the user point of view. Under the hood, we have a kind of query plan that'll look sort of roughly familiar to those of you who have worked in query plans, and a variety of execution strategies. And then we've built a few different interfaces to the system, a textual interface, graphical, and an API. And I'll be showing you the graphical interface as part of the demo at the end of the talk. We have focused on relational streams, and I think relational streams are adequate for most applications we've looked at. We're not doing the multimedia, so streaming media is a totally different thing despite the fact that it uses the same word. We have focused on a centralized DSMS. So we've been looking at a server model very similar to a typical DBMS model. Were we to continue work in this project, I think distributed processing is the most important next step. Because a lot of applications, sensor applications, even web tracking people's browsing behavior, for example, are inherently distributed. You want to put little DSMSs at tons of different sites and maybe a heavier duty one centralized. So we haven't done that, but that's a great next direction, I think. Okay, so any questions so far? No? All right. So what were the challenges that we looked at? Now in retrospect, I can tell you what our challenges were. I'm sure I could not list these at the beginning of the project. So challenges in retrospect, trying to categorize them. One of them had to do with just the stream rates. So one possibility, not of all applications is this true, is that we're looking at very high stream rates or rates that vary a lot over time or are prone to sudden bursts. And the data itself, we don't really always know what's coming, so unpredictable variable data. And then we want to look at query loads that also can vary, and not so much in number of queries, maybe in number of queries, but also in complexity of queries. So we have a very rich query language. You can express very complicated queries. Now, another way to categorize this, probably makes even more sense, is one of the issues is overload. So what happens in the system when suddenly it's overloaded because the stream rates are too high, or there's too many queries, or they're too complex, and you start getting behind, for example. And the other half is changing conditions. So because we're working in a continuous world with continuous queries and streams, things may change over time. It's not like a traditional query where you look at your statistics, you figure out how to run your query, you run it, and you're done. Maybe you'll run the same query later and the statistics will have changed. You at that point can re-optimize. But we're talking about putting in a query and maybe it's going to run for days or months where there may be significant changes to the data or especially to the system that you're running it on during the lifetime of the query. Okay? So what have we done to address these challenges? What are the features of our system? Well, one thing that we do is we are able to share state and computation among lots of different queries. And I think many of you may have heard Arvind's talk where he talked in detail. So I'm giving sort of a high-level project talk, and one of my students gave a talk 3 months ago or so, very detailed on this particular aspect of the problem. We also look at resource allocation is very important. And again, it's because we don't have the get in and get out model. So if you're running a one-time query, it may grab tons of resources to do its work, but then it's going to get out and it's going to release those resources. If you register a query that's going to be around for a week and it grabs a lot of resources, then you're in trouble. So you have to really be careful about that. More careful, I argue, than in a traditional system. Then in terms of dealing with the changing conditions, we've done quite a bit of work on adaptive algorithms. So having the system monitor how it's doing and, for example, re-optimize or reallocate memory because something has changed since you started up that query. And then, as I mentioned before, we've looked at approximation techniques where when the system is overloaded, or maybe because the application just doesn't require an exact answer, we can minimize the work or minimize the memory used and give close to exact answers, but not absolutely exact. Okay? So let me tell you what I'm going to do in the rest of the talk. I'm going to first talk about the query language itself a little bit and give a few examples. Then I'm going to show you what our query plans look like and how we execute them. Then I'm going to talk about these two issues, the overload issue and the changing conditions issue. I'm going to just capture a bunch of pieces of work. There's been a whole lot of papers. I'm not going to go into great detail on those. And then I'll give you the demo. So I'd be happy to talk about any of this in more detail while I'm here. Yeah?
Does the user have any sense of how long the query might run? So if he knows it runs a week, he might not want to run it. And along with that question, is there any way for that user to look at his query and how it's doing it at some particular time?
Right. So does the user have a sense of how long the query is going to run? Absolutely. The user is the one who registers and deregisters it. I think what you might want to ask is whether the system has a sense of how long the query is going to run. And no, we haven't worked on that. So the assumption is when a query is registered, it will be there forever. That's our assumption. We don't do any optimization, say, knowing it's going to only be there for a day or 2 minutes. Okay? The other question was, can you look at a query and how it's doing? Well, you can certainly look at the answer to the query, but I'm also going to show you that we have a pretty nice system for we have a pretty nice subsystem for monitoring query execution and things like resource use, and I'm going to actually do that as part of the demo. Yep, and you can also look at the query plans. So, yep. Any other questions? Yeah.
Well, while we're on the topic of what the system knows when it's doing its optimizations. You're going to talk about how streams have highly variable stream rates and can get bursty. Does the system take any advantage of known regular streams, like streams that have fairly fixed frequencies?
The system steady state sort of assumes that. So yeah.
Okay.
Right.
Okay. So since that's the easy case, there's no reason to explicitly convey that information.
That's right. What the system does is it has a notion of how things have been behaving recently, and it executes under that assumption, but it also keeps an eye on things to see if they change. Let's put it that way. I guess I see. If you knew that things weren't going to change, then you would not have to do the monitoring to see if they were going to change. And maybe that's what you're getting at. There's actually this interesting notion of adaptive adaptivity. I like the name. I didn't invent it, by the way. Invented at Berkeley. So adaptivity is the system monitoring itself and deciding when it needs to change. Now, a system can also monitor the rate of change. And so it can adapt how much it needs to adapt based on how much it thinks it's going to change. Everybody follow that? It's actually a kind of cute thing, and I think deserves some work. Right? Not much has been done, but it's a cute idea. Okay. All right. Ready to delve into the language? All right. So the language is called Sequel. Sorry. It's supposed to be my best joke. And now, okay. So the language is called Sequel, CQL for Continuous Query Language, not to be confused with SQL SQL. And in fact, we started with the SQL Sequel, and we added just a few things, but a few important things. First of all, we added a new data type, streams. Obviously, we're going to need that. And you're going to see streams appear in the from clause, just like relations typically appear in the from clause. We needed to change the semantics from the typical one-time semantics over a static database to a continuous semantics, and that was the hardest part, really. We have windows on streams. Many applications are interested in looking at, say, the most recent 5 minutes of the stream data or the most recent 200 measurements, that sort of thing. We didn't invent anything new. There's a windowing language in SQL 99. It's actually designed more for sequence databases. A sequence database, by the way, is a traditional database where the data elements themselves have an order. Okay? That's different than a stream database. A sequence database is still much more traditional in style, where you just do a query over it. But there is a windowing sub-language for sequence databases. And then we have a very, very basic sampling. So don't even ask me about sampling, especially you sampling experts out there, because we just have a little operator that will do random sampling if you want to reduce the rate of your streams. Again, taken from the standard, but nothing exciting whatsoever. And then we have 3 operators that will take relations and turn them into streams. And this turns out to be fairly useful. So I'll show you those. And that's all the extensions we've made to SQL Sequel to get our language CQL. We have a few shortcuts and defaults just to make things look clean. What's more interesting, I think, is the equivalences in our language. So obviously you need equivalences if you want to do query rewrite optimizations, change a query to an equivalent form that may be more efficient to execute. Because of the way we designed our language as a strict extension to relational languages, which I'll show you in a moment, we do have all the relational equivalences in our language, and that's really a nice feature. So we can use all rewrites from traditional databases, and then we have new equivalences based on streams. And the way we approached the language question actually was to define an abstract semantics. I'm not going to go into this much at all. But what I mean by an abstract semantics is we take the relational query language as a black box, and then we add the windowing operators and the stream to relation operators. Okay, sorry, the windowing operators, the relation to stream operators, and define a continuous semantics that way. That means that I can give you a CQL for relational algebra, a CQL-like language. You give me your relational language, I will give you a stream language with continuous semantics. Okay? The one I'm going to show you is the one that uses SQL as the relational language, and that's the one we've implemented. But we decided to approach it from a fairly abstract way, and we're glad we did it that way. Okay, so let me just show you some examples. I'm going to use 2 extremely contrived streams. You would probably never write this as a streaming application, but it's orders and fulfillments. An order has an order ID, a customer, and a cost. Fulfillment is an order ID being fulfilled by a clerk. Okay, again, just for something we can easily understand. And the first query is totally contrived as well, but it shows the language, a few of the constructs. Let's suppose that what we want to find out is about the orders that the clerk named Sue fulfilled over the last day for a customer named Joe. And here is the query in SQL. Let me walk you through it. So in the from clause, we actually have two streams, the orders stream and the fulfillment stream. And I'm interested in fulfillments over the last day. So I put on there a window range 1 day. Okay? We have range windows that tell you a time period. We have row windows that tell you a number of data elements. Okay? And we'll see examples of both. This says look at the last 1 day of fulfillments. Join it with the order stream, okay, on the order ID. Make sure that the clerk who fulfilled the order was Sue, the customer was Joe. So now I have the set of orders that happened in the last day by clerk Sue over for customer Joe, and I take the sum of those. Okay? Is that pretty clear? Okay? No big deal, except we spent months working on it. But okay, yeah.
This is going the size of the orders table. If you don't have put a constricted window on it, will grow indefinitely, right?
Yep, the one that I referred to here grows indefinitely, and I'll tell you a few things about that a little bit later.
So this query can't run, right?
This query can run. So let's see. I wanted to keep things simple. Typically, you would want to window a query, but what we would do here, theoretically, is that we can detect that when you have orders and fulfillments, there's actually a temporal correlation between those, and you don't have a lag more than, hopefully, a few days. And therefore, you can throw away the orders that are more than a few days old. And we actually, I'm going to get to this very lightly, have done work on referential integrity constraints with time delays between streams, detecting them automatically and using them to throw away data. Okay? So that's what optimistically would happen here. Realistically, better ask the user to put a window on there. Yep.
Yeah, I was going to sort of ask the same question, but the range 1 day starts. In real life situations, these things are typically produced in different legacy systems, and the data flows not in monotonic order, but in, you get packets. I get a little chunk here, a little chunk there, out of order. And all.
I've got a whole couple of slides on that issue.
And it can take months for some of the stuff to come. So the question is, and also the clocks are out of sync.
Yep.
So so this range 1 day.
Can we come back to it?
All right.
I do have 2 slides and a whole paper on this issue. Right. But we're only getting 2 slides today, and you can get the paper too.
Question about the semantics of that.
Yep.
This sum of cost, how does it get to the user? Is it output stream?
Right. I'm going to come to that in about 2 slides. So you have to wait like half an hour, but you only have to wait 2 slides. Yeah. Okay? Next example. Again, totally contrived, just showing you some of the other features of the language. This one says, I'm going to take my fulfillment stream. I'm going to sample it for whatever unknown reason, take a 10% sample. And then I'm going to look at the 5 most recent fulfillments per clerk, okay, and return the maximum cost. So I'm sampling my stream for unknown reasons, and then I want to look at each clerk and the most expensive fulfillment they've done in among the last 5 that they've done. Again, just to show you the constructs. So here's my 10% sample over my fulfillment stream, just random 10%. Again, don't ask me about sampling. This is a special kind of window that actually does a sort of group by within the window. So this says take the stream and imagine you've split it into tons of substreams grouped by clerk. So now we have a separate substream for every clerk. From each of those substreams, take the last 5 fulfillments and mush them all back together. Okay? So now I've got the last 5 fulfillments from every clerk. I join it with orders as I did before. Okay? And then I group by clerk. Now you don't have to have the same attribute here that you had in there, but that's typically the kind of thing that happens, okay, in the queries. So now I group that chunk by clerk, and I return the clerk and the maximum cost. Okay? The result type question, you asked if it was they get it as a stream or as a table. So the way the language is defined, and by the way, so the way the language is defined, it actually, again, we have an algebra, and every operator takes streams or relations and produces streams or relations. Now, so that the output type of a query is defined by that semantic. So let me talk about this one. This is a simpler version of the query I just did. This says take the last 100 fulfillments, okay, just all of them, and join them with orders grouped by clerk and take the maximum cost. So this is the maximum cost of an order fulfilled by every clerk within the last 100 fulfillments. Okay? The result happens to be a relation, actually. The definition of this query, because it's non-monotonic, says that I'm going to have a relation that contains the clerk and the maximum cost over the last 100 fulfillments. And if that value changes, then I'm going to update my relation. Now, frequently you want it to be a streamed result. And actually, we do that with this operator called IStream. I mentioned these operators that take relations and turn them into streams. So IStream stands for insert stream. And all it does is it takes a relation and says, I'm going to take that relation, I'm going to turn it into a stream of all the inserts into the relation. Okay? That's all it does. So dstream takes all the deletes to the relation. Okay? So these are handy operators. All right? So in this case, every time a clerk has a new max, that would be emitted on a stream, and we have a streamed result. Okay? Now, I'm going to show you something really cute, actually, we can do. This is my last example query. And this query shows how we can take our language and use it to run historical queries over normal relations. Okay? So in this query, we have a plain old relation, no streams in sight. This is a relation that contains, at any given time, the current price of stocks. So it has for every stock the stock ticker name and the current price for that stock. And I can use SQL to give me the average price over the last day for every stock. Okay? And here's how I do it. I take the current price relation and I apply one of these IStream operators. And now what I have in my from clause is a stream. It's a stream of all the new values that have been inserted in there over time. I take the last day on that stream. So now I have the last day's worth of prices. I group it by the stock, and I return the average for that stock. Isn't that cute? Right. Okay, so everybody pretty comfortable with the language now? Yep.
For the input stream, can you handle update and delete, or they are just like an insert?
Our stream model is just, the formal model of a stream is a tuple timestamp pair. Okay? That's it. So it's all inserts, if you want to think of it that way. And we'll come back to timestamps later. Yes?
I looked at this example. Where's the time information coming from?
So the time information, okay, yeah. The time information is not obvious here. So, and I'm not going to go into time in detail, but when you do a relation insert, delete, or update on a relation, it's time-stamped. When you do an IStream operator, it carries the timestamp of that operation. So that's a very good question, actually. So when there's an insert or an update in current price, and I get my IStream, it will emit the time at which that happened. Okay? Yeah. Yeah.
Maybe related, but if I apply an IStream to a normal relation, am I always getting the same order, or will it be non-deterministic?
You will get it ordered by the time. So we assume a discrete time domain, and we assume that every operation happens at a time. Okay, but not just one at a time. You can at a given time you can have multiple operations. So the stream will be ordered by the timestamp, but within a particular time it could be in any order. Okay, that makes sense? Yeah.
So how did you decide what primitives to put into the language, and how can you decide when to stop? We don't need more primitives.
Right. Well, so our language is pretty expressive. We have all of the relational primitives at hand. I don't really have a good answer for that. We did study a bunch of applications, and actually we curated this repository of stream applications where we wrote a whole bunch of queries in our language, and it seemed good enough. There are a few things that we can't do, a few pet things that I could talk about offline or at the end of the talk if there's time. You're not asking about time again, are you?
Well, slightly different. Electrical
Okay.
engineers would like to do things like convolved by a window and maybe not a rectangular window. Do you support that kind of thing?
What does convolve mean? Am I the only one in the room who doesn't know what that means?
Right, it would be in the first course in electrical engineering. It would be.
I've yet to take that, despite the fact that I have a joint appointment.
So, what you have here is...
But I never took biology or physics either, by the way. I was just a music major. Yeah. So, are you talking about the way the window slides?
No,
Or
it's the shape of
the shape of the window?
So typically windows wouldn't be rectangular, but they might be some other shape.
But, well, we're linear here, right? So it wouldn't be a contiguous sequence of events. Is that what you're saying?
No, it would be contiguous. we better take it over.
Okay. Well, let me just say one thing. Our abstract semantics, actually the window operator can be anything that turns a stream into a relation. So it doesn't have to be a window at all. Any function that takes a stream and a time and gives you a set of data, we call a window. We happen to have implemented a very simple sliding windows that slide either based on time or on number of rows in our system, but we will happily take your function and turn it into a window and stick it in our query language. We won't optimize it efficiently, just like typical function, when you make function calls, they don't typically get optimized. But we can take that in our language, and as long as it produces a set of data, we're fine.
So I have a question. Can any of the queries which a user registers, can they change the data? Like, can they do an update or insert or delete?
Stream data?
On the data?
They could generate a new stream. So yeah, I mean, you can go stream to stream. So if you call that changing the data, sure.
So let's assume I have a stream. So the first user, he registers the query, he looks at the stream and he deletes the tuple, whatever is the corresponding message is. And then there's another query which sits after that and supposed to read that.
No problem. The first one's a view. Second one uses the view. Does that work? In fact, no?
Very clear, yes.
So I make the first query that transforms the stream into a view. It's a view that produces a stream. So now I have a named view, V, and then I use that view in the other query as if it's a base stream. So we do have views that we can use as base data, both relations and streams, in the sense that a traditional system uses them. It's actually very powerful, and I'll show it in the demo. IStream is an interesting operator. IStream at every time step streams the entire relation. And it turns out to be pretty useful, but I'm certainly not going to have time to explain why. Okay? So it just plops out the whole relation at every time step. Yep. Any other questions? Yes?
I don't know how, for example, whether your system has like limitations. So like say, if users specify like I want the average every minute. Another query say I want every 30 seconds. And another say every 3 minutes. User can specify any of that kind of condition. I mean, then your system is probably very hard to handle lots of those queries.
So actually it can't do that, and that's one of the things that it should be able to do. And I don't want to go into this in too much detail. Right now, we generate a stream element every time something changes. Okay, so it's not that you get the average every minute. You get the average every time the average changes, every time, say, the window slides. Okay, and the window slides every time step or every time there's a new row. What we've defined in the language, but have not implemented, is a slide granularity. And I think that's sort of orthogonal to the window size. So I think the right thing that you want to have is you want to have a window width and then how often you slide. Okay? And there has been some work on that area. The other approach you can take, which Arvind I think may have talked about, is that your window slides but you never generate any answer except at random times whenever you want you can probe and get an answer. And that's the most general. So in our system, you get an answer every time the window slides. Other possibility, periodic, you specify a granularity. Most general, give me an answer whenever I ask, and I could potentially ask every time the window slides.
So is it possible, for example, if the query is fairly complex, so you couldn't even finish evaluating the query for that during that period?
That's overload. That's overload. I'll talk about that a little bit. Okay. We made it through the language. Next, let's talk about execution. Okay. Oh, we didn't make it through the language.
Yeah, I was hoping you would answer this in the next slide, but you said to output streams you have this IStream and this DStream. Do you have any other way to output streams?
RStream. Nope. Well, if the query is monotonic, it gets a streamed result anyway.
Well, that's the part.
In fact, the secret is everything is a stream. A relation, an output of a relation we actually model as inserts, deletes, and updates streamed anyway.
So from the point of view of the user, this distinction gets made?
Well, that's what the API looks like. Right. We should take this offline, I think.
Okay.
Yep. Yep. Okay. All righty. So what do we do when we get a query? Well, we generate a query plan, just like everybody always does in a database system. We might have many other query plans running at the same time. So the new plan, as much as possible, is merged with existing plans. Now, that's sort of a myth. Our system does very minimal automatic plan merging. Streams are shared by everybody, okay? But other than that, nothing automatic happens. We have ways for users to go in and move around pieces of query plans so that we can experiment with merging, but we don't do a lot of it automatically. Plans consist of operators, queues between operators and input queues, and state. Okay, nothing dramatic here, and we have a scheduler for execution. So here's a simplified version of our query plans. We'll see live plans in a little bit. This is 2 queries. Q1 is doing a join of stream 1 and stream 2 with a selection on top. Okay, and so here we have the 2 streams coming into input queues. We have a join which needs to maintain some state. Writes to an output queue, and query Q1 applies a selection on that, and that's the end. Q2 is a 3-way join. It's sharing the join of stream 1 and stream 2 with Q1, and might actually be at a different place in the output queue there, and it joins it with stream 3, keeping some state, and that's what we have. And then we have a scheduler that goes around and tells the operators when to run. When an operator runs, it reads data from the input queue and writes data to the output queue. That's the processing model. Okay, so what about memory? The queues involve memory, and these little state things involve memory for the joins, and this memory is going to stay there indefinitely, so we have to be careful about it. Our project, we kept all that stuff in memory. We did not use disk. Definitely it's interesting to figure out how to write this stuff off to disk when it gets too big. We just focused on how do we keep this small, but I will tell you right now, sometimes you're going to have to write it off to disk eventually. So our goal was to use as little memory as possible, but still produce accurate answers and not fall behind. Okay, so we have 3 ways of reducing the memory. One of them is one I alluded to with this referential integrity constraint stuff, which is that we can detect when there's patterns or constraints on the data in the streams and use that to reduce state. And I'm going to give you a couple quick examples. We also try to share state as much as possible within queries and across queries. And then we have a scheduling algorithm that's goal is to minimize the sizes of the queues. Okay, the constraints. Let me talk about this pretty quickly. So if you take our queries and just look at them the way they're written, they may require unbounded state. As you said, you can never execute this because the state grows and eventually you just run out of memory. That is for arbitrary streams. In reality, streams are usually not arbitrary. So streams may have certain constraints on the way the data arrives that allow you to dramatically reduce the state that you need to keep. You realize you're keeping state that's useless and you can throw it away. There's a whole big paper on this, so I'm not going to go into this in detail. The kinds of constraints we looked at were clustering, all the values for this order are going to come together. Or ordering. I know I'm getting something in a sequential order. I'm never going to see an earlier value, so I can throw away anything that would need that earlier value. Or this notion of referential integrity between streams. Now, one of the big differences is we're not enforcing these constraints. We're detecting these constraints, and usually they're not 100%. So I may get my streams that are roughly all the pieces of an order are roughly together, but they're not exactly together. So what we do is we define this constant k that sort of says how close we are to a perfect constraint. If k is 0, then I've got a perfect constraint. If k is 100, it means I might have 100 other elements, say, mixed up in my clusters. Okay? So it quantifies how closely I'm meeting those constraints. And again, I can't spend too much time on this, but one example is if we're, say, fulfilling our orders in many pieces. Okay? The first example, you fulfill it once. Let's say it's in many pieces. If we know that all of the pieces of a particular order are clustered in some, k cluster, they may be within 3 days, I'm going to always fulfill an entire order, then that can tell me when I can throw out orders, when I know I've finished the entire order. Okay? It's, again, a very contrived example, but it gives you the idea. So what we do is when we have queries, we know what constraints would be useful to those queries, and we monitor the data to see if it satisfies the constraints. And if it does, then we can use that to reduce the state. Now, one nice feature is that if we think a constraint is going to hold because it held before and it stops holding, we get a quote-unquote approximate result. So I like to call it approximate. It's actually wrong, but it's an approximate result. And the error in the result is exactly proportionate to how much the constraint got violated. And then when you see that violation, you can change your constraint and start keeping more state. Okay? Fairly clear? All right, briefly talk about state sharing. As I said already, input streams are shared by all queries, so we're not going to demultiplex the streams immediately. For every stream, we keep the maximum window required by any query over that stream. Everything else can be tossed. We can also, I already said this, we can also, when you have matching subqueries, you can share all the processing, but we don't do that automatically. It's a tough problem. We do have sophisticated techniques for sharing for certain class of queries, and this is what Arvind talked about. Okay, so reminder, this is what our query plans look like, and I'm going to tell you a little bit about the scheduler, not a lot about it. So the scheduler is going to go in and it's going to run the different pieces, the different operators in the query plan. The way it works is every operator it has a method called run and how long you want to run it, a time slice parameter. Now scheduling in stream systems is actually a pretty interesting problem, partly because nobody knows what the objective is. So it's not necessarily throughput. In regular systems you can say, well, maybe it's throughput or response time. I have a pretty good notion of what my objectives are. Here it could be latency. How soon from the time a tuple enters the bottom of a plan does the result come out the top, for example? Or how much memory you're using could be an objective to reduce memory use, or computation. Or if you're approximating, maybe you want a schedule that minimizes the inaccuracy, or you don't want to starve any queries. So that's really a different issue. We have 4 scheduling algorithms. The one that's implemented is the very exciting and sophisticated round-robin algorithm. The one that's published is the minimize queue sizes algorithm, pretty interesting algorithm that guarantees to keep the queue sizes small to minimize memory use. Unfortunately, keeping the queue sizes small happens to have a side effect of increasing latency. So the one that minimizes queue sizes seems to maximize latency. We have another one that tries to minimize a combination of queue sizes and latency, and then we have the one for running queries in parallel. All right. That's it for state. Let's talk a little bit about overload. So there's this term load shedding, which has to do with throwing away data because you're too busy to deal with it. Okay? So load shedding is what you do when you have overload and you're willing to discard data and get approximate answers. So if you're going to do any load shedding at all, if you're in an overload situation, the goal is to figure out the best approximate answer that you can produce without allowing all the data to be blocking up the input queues, without ever falling behind. And actually, Utkarsh has worked on this problem. And one of the first things he said is, well, what's the definition of best? That's not even completely clear when you're trying to approximate. So one definition of best might be, I want to get the maximum subset of my answer. So I want my answer to be as big as possible. But it turns out when you do that, you might actually sort of bias your answer, because I might keep the data that's going to generate the most answers and throw away the data that's going to generate the least. But what if I cared about those outliers? Very often that's actually what I care about, and this is a bad idea. So another way you can approximate is to say, I want to get the maximum random sample guaranteed of the answer. And these lead to different algorithms, so it's fairly interesting. And again, we have some results that Utkarsh has published for specific query types. We have not solved the load shedding problem for the whole query language. That's very, very hard. Okay. Changing conditions. So I've alluded to many times that we want to deal with the fact that we register a query, and then as the query runs, things change. The data characteristics may change. Somebody might have registered more queries. Now the system is more overloaded. Maybe someone added more hardware, so the system is more powerful. All kinds of things can change. So what we want to do is monitor the system and then adapt the way we're executing our queries accordingly. And I'm not going to, multiple papers on this topic, I'm just going to allude to it briefly. We already saw one example of monitoring the system and adapting what we do. Anybody remember? First quiz. Actually, it was the K constraints. So when I said we want to look at we want to monitor the data and see if it satisfies constraints, and when it does, we can throw out state. And then if we discover that it stops satisfying those constraints, we have to change our strategy and start keeping more state. So that's one example. We also have algorithms for reordering operators. So we might order our operators a particular way because of the data that we're seeing or the arrival rates that we're seeing. And then as that changes, it might actually be useful to swap the order of the operators. We also have a mechanism for caching substate and query plans, and again, we do that adaptively. In fact, I sort of got to be convinced by this whole adaptiveness is that this notion of query optimization, the way we're doing it in the database community, is all wrong. We shouldn't think about a query plan for so long and then produce one and just let it run. In fact, we should just produce really dumb query plans, and they should monitor themselves and just reorganize to be the optimal plan. So that's certainly an extreme notion, and you don't always want to do that. But it's actually pretty effective. I'm starting to be a believer in adaptive algorithms. Okay, so let me just skip this, actually, because I hear you want to hear about time. So let's talk about time briefly. Time has turned out to be one of the real nits in our system, how to deal with timestamps and temporal consistency. This is, again, work that Utkarsh has done, so you can ask him all the hard problems. But let me give you an overview of the issues. So our model is that stream elements have timestamps on them. Okay, so the model of a stream is that you get a tuple at a particular time out of some time domain. So there's one time domain that we're working with, and we're just going to assume that. And we need this notion of time for a couple things. We need it for time-based windows. So if we're going to say last 5 minutes, we need to know what does that mean looking at these timestamps on the elements. We also need it for a consistent semantics over the whole. You asked the perfect question about where did I get those timestamps on that price relation. We need to have a notion of time that permeates the entire query, not only for the streams, but also when relations get updated. So time is pretty intrinsic to the semantics and to the query execution strategy. Now, everything works really well. You can just sort of do the expected query processing when you know that all these stream elements are going to arrive at the system in timestamp order, and I mean globally. So I'm going to get everything is going to come in a nice, perfect order, okay? Then we have no problem. And that works really well if the time that you care about is the time the streams arrive at your system. Okay? So if I timestamp when I get something in the system, it arrives, then I'm going to obviously trivially have this property. The problem is that that's often not the case. If you think about a sensor application, just about any monitoring application, you're actually getting timestamps from the application itself. And that's when you get into trouble, because you can have elements arriving out of order for various reasons. They can be really out of order, like he says, lag of days. You have streams coming from different places. It takes different time to get there. You can have reordering as elements are sent to the system. So here is a one-line summary of a whole paper, which is that our solution is to have a notion of heartbeats, where when we get a heartbeat from a particular stream, or when we deduce a heartbeat, one way or the other, we either get it or deduce it, that tells us that we have now seen that when we have a heartbeat at time t, we are no longer going to see any stream elements coming in with a lower timestamp. Okay? Once we know that, then we're in good shape. We can design buffering algorithms that are going to buffer the data and then send it through with that property that we're seeing it in order. Okay? And so some of the work we did is how we can monitor the streams coming in and deduce heartbeats based on the behavior of the skew we see between the streams or how long, the pauses that we see. Now, once again, if we make a mistake in deducing the heartbeat, we get an approximate answer, okay? Error. But this approximate answer, again, is going to be the degree of approximation, or the degree of inaccuracy is exactly related to how big a mistake we made in generating a heartbeat. Basically, we are going to get data that we're not going to be able to process. We should have been able to process it, but we said, oh, we're already past that time. Okay? Yeah?
The time is correct, which means that if some clock is 1 minute off, what would be...
No, we are assuming accurate clocks. So we're assuming a global time domain that everybody understands. Yep. Okay. Just a little bit of social stuff about stream system work, and then we'll get to the demo. So during the time we were doing this work, there were basically 3 systems being developed, 3 general purpose data stream systems. Ours work in the Northeast started by being called Aurora and then Borealis, and now they are commercializing in a product called Streambase. And over in Berkeley, a Telegraph project. Now, one nice thing is that actually in these projects, we had periodic meetings about every 6 months. We were pretty friendly. We talked to each other about what we were doing. We had this Stream repository of applications that we all shared. We also talked about benchmark. It ended up being the Northeast group that developed the benchmark. But we are running the benchmark, and I will show you the benchmark running. The main goal of the benchmark was actually not so much to compare stream systems, but to prove that stream systems were necessary, that if you tried implementing the same benchmark on a conventional system, it wouldn't work. The Northeast people did implement this benchmark on Oracle using triggers, etc., and say that it's 5 to 10 times slower. On the other hand, they implemented it and wanted it to be slower. So on the other hand, our system is order of magnitude, I think, faster than their stream system, so maybe 50 times slower than their Oracle implementation. So anyway, I don't know how strong an argument that is. The benchmark, let me just tell you about it very briefly. The benchmark is simulating a system where cars that are driving on roads have little transmitters on them, and every 30 seconds say, here's where I am and here's how fast I'm going. Okay? This benchmark itself, the simulation, is a little bit limited in that it's linear city, which has 10 parallel roads, and that's it. So you can drive down one of these 10 roads, and you can get off or on, but then once you can never change from one road to another. That's really not very relevant. What's most interesting about the benchmark are the queries. And the most interesting query is one that's called variable tolling. And this is actually something people are talking about doing, which is automatically charging people tolls dependent on who you are and especially the road conditions at the time. So every time you enter a new segment of road, automatically there's a toll calculated based on how congested that segment is now, the history of that segment, whether you have a frequent driver discount, and so on. So in this benchmark, these Northeast people described all this in English. And then we implemented in our query language. And so it turned out to be a fairly interesting query. And I will show that to you when I do the demo. The stream is a stream of cars, how fast they're going, where they are, what lane they're in, and so on. OK, so I'm going to do the demo. I'm actually going to swap machines because my machine doesn't connect to the internet. So this is where you brought yours, right? OK, so I'm ready to swap out. What I'm going to show you is streams coming into the system, continuous queries executing over those streams. I'm going to show you our query plan visualization system. I'm going to show you how we can monitor our system using introspection, which I think is one of the cuter parts, and then I'll run the benchmark. So while we swap, let me just thank a bunch of people. The Stream project obviously had a lot of people involved. Here's a whole list of students and such. If you want to find our homepage, from which, by the way, you can run exactly the same demo I'm going to run now. You could run it along with me if you want. Or you can download the code. Just type Stanford Stream and you'll find us. So any questions while we swap in a new machine?
So when you compare, when you created the benchmark, how is the notion of approximation captured?
There is no approximation of the benchmark. Yeah, so the benchmark, in fact, what the benchmark does is kind of interesting. The answer to the benchmark is a number, which is how many expressways of data you can keep up with without falling behind. Approximation is not allowed. So you have to compute these tolls, and you crank up the number of expressways and see how you can keep up with the tolls. So, and just to brag a little, they have a data generator, and they haven't been able to generate enough data to saturate our system yet. So, but they're busy starting a company now. So, yeah. What? Okay. Yeah.
Oh, I just have a small question about the comparison. You're comparing it to Borealis?
Aurora.
Oh, okay. So that was the non-distributed version.
That's correct.
Okay.
Doesn't make a difference. The benchmark is centralized.
Okay. I was just wondering if there's overhead in their system because it was a system that's built to handle distributed.
No, we compared it to Aurora.
Okay.
Yep. Yes.
So in a real-life situation with orders and fulfillments, both are coming in constantly, and you never have seen all of either one. So there's no lag in which I can say at this point you've seen all the fulfillments. They're only going to be at most 6 months behind. I mean,
correct.
Some of them are still take years to happen. And the kind of question people want to know are statements about average lag and and how much is. You want to know in the limit how much is ever going to get fulfilled? What's the loss? What's the shrinkage? And so can you state, do you have ways of
Well,
stating?
if that's your problem, you probably don't want to be using a stream system. What we're about is online rapid answers.
Well, right, but if you want to know what the lag is, that's an online kind of question. Are we catching up or are we losing ground?
Okay.
That's a common question. What's the average time to completion? That's a kind
Well,
of
average time to completion is no problem.
Oh, no, but you want to know, are you making progress on that?
Trajectory of the average time to completion is not a problem either. You could generate a stream that's the average, you could generate a stream that's the average time to completion and then put over that a query that monitors the trends in that stream. We should talk offline though, I think. That's because I may be missing that. We should try to write the actual query you have in mind. I think it might be helpful.
Change the focus to the...
Oh, okay. That'll be fine. All right. Let me tell you what we've got here once I get rid of all of the Karsh's window. I didn't show anything I shouldn't have shown, I hope. Is this... Oh, wait. Okay. We're having a problem here. Connection closed. Okay, well, let's... Oh, now we just... Something's not going well here.
Okay.
I think that... Where did that other... yeah, so this is the problem. All right, we're starting over. Were you using Internet Explorer?
Yeah.
No wonder. Okay. All right, so Stanford stream. What you type, you go to the first hit, you find this click here. I'm just showing that you guys can do this too. You start the server. I just started a server at Stanford for this particular demo, and you can do the same. All right. Now we are in good shape. I think. Yes. Okay, so what we've got here is a big white pane in which I'm going to show you query plans. We've got a bunch of buttons where I'm going to do various things. We've got a little legend about what the query plans are about. And again, you can do this at home. This is running on a dedicated server. So under the demo, we have a few predefined scripts. I'm going to register a couple of streams, two very exciting streams. They're called R and S. And there we go. The schema of the streams is shown here. Is that too small, or are you okay with that? Okay, the schema, each stream just has a name and a value, okay, for these queries. I had a little script that registered those streams. If you want to register a stream yourself, you hit register stream, you give the stream a name, and you give the attributes, etc. It's schema. The other thing that this system allows you to do is you can bind a stream to a file, and that's already been done for these. So what I actually have is a file of name-value pairs for stream R and one for stream S. And when I start up the stream, it's just going to read those and loop forever. Okay, and I can control the speed of that. So that's how I'm going to stream data into the system. Okay, so I've got these two streams now defined. Now I'm going to register a query. What do you think I should register? Any suggestions? Select star from S? That's always the one I start with. Okay, so let's do select star from S and see what happens. So we register the query. Now I generate the query plan, and that's all set. Let's take a quick look at the query plan here. So here it is, pretty exciting. We've got the input, and we've got the output, and a little queue there. Okay, but you can get some information on the pieces of the plan. For this just tells us the ID of that operator. Sometimes there's more information with particular operators. Okay, so I've got select star from S registered. Let's go for it. So we hit run. And we get this window here that's going to get the answers to the query. Is going to just spew out in this window. Nothing is happening yet because stream S hasn't been started. I start up stream S, and now we see, ta-da, select star from S is working. And now we're seeing the output. So this is, again, this name and attribute. Now I can crank up S if I want. Now you can see that it's cooking with S zooming through. Yes?
Why do you need the store on top of the input?
It's about every input. Every stream is buffered on the way in because it can be coming from anywhere. So we assume that the stream is sort of pushed in, and then we have a buffer, and then we send it through the query plan. We also need to buffer it for this time stamping business if we need to reorder things. Yeah, so just generally, yeah. Okay, So that was select star from S. Pretty exciting. We'll pause here. We'll drop that query. Let's do something a little more complicated. I'm not going to type in the queries anymore. I've got a few scripted in here, and you'll see the same menu if you try a simple aggregation query. So this is going to still use our stream S. It's going to put a 15-second sliding window on it. Okay, so it's 15 seconds wide, slides at every time step. It's going to, within that window, group by the name and give me the average. So it's going to be a running average, a sliding window average for every name in the data. Okay, so I'll generate the plan. I'll take a look at the plan. It's a little more complicated now. We have a time window and an aggregation and various other operators I'm not going to have time to explain in the remaining 6 minutes. And so let's start that one up. And it's not going yet because the stream isn't going. Now the stream is going. Okay. Now let me just say a little bit about what's actually coming out here. The actual, technically, the result of this is a relation, because at any point in time it's the current name and the average, the moving window average. But we implement that as plus and minus stream. So what you're seeing, every plus here, actually you can see every plus here has a minus that goes with it. And that's showing you the new value when the window slides for that name and the old value going out. So that's the most general. If I wanted to get rid of the minuses, I could just put an IStream on that query, and then that would effectively get rid of the minuses. Okay? So actually, let me pause that, and let's drop this query. I can run a couple of queries at once. Yeah, I think I'm going to skip that part of the demo. I usually just show the select star from S and the aggregation at the same time. And isn't it exciting? You can see the data come out at the same time, and the timestamps are coordinated. I will skip that, I think, for the purposes of time. So let's go on to a join query, which is more exciting. Okay. Okay, so this query is going to take the join of streams R and S. It's going to take a 200-row window on R. It's going to take a 20-row window on S, and then it's going to join those. Okay, so these windows are sliding on both of them. It's going to join them, just random join condition. It's going to, when they have the same name and the R value is higher than the S value, that's going to be a match for the join, and it's going to spit out a result. Okay, so let's generate the plan for this one. Let's take a look. So now you can see this happens. This is the R side here, which we can see. And over here is the S side. We have a window on both of them, the join operator, and then the output. Okay? So let's run this one. Here's where the results are going to come out. Nothing is happening yet because no stream is running. I start stream S. Still nothing is happening because nothing's happening on R. Now I start R, and we start seeing data come out. Let me increase R a little bit. Okay? We should see more data coming out. All right, so that's a join query. Now, next thing I'm going to show you, any questions, by the way, so far? Yeah?
How do you compute the timestamp of the joining tuples? What's the semantics?
Right, so the timestamp, the semantics are that the time at which the join tuple is produced relative to the time of, the simple answer is it's the maximum of the two timestamps, but actually I can sort of derive that formally for you using our semantics. Okay, so because we have formal semantics for the time on an updated relation, and this is when you're joining two things, you're doing an update. But anyway, the simple answer is that the time at which the join tuple is produced is the later of the two joining tuples, which makes complete sense because you don't get the tuple until that later one is produced. Does that make sense? And for aggregation, it's sort of the same thing. So when you say slide a window, the time at which the window slides is the timestamp on the insert, new insert. May seem counterintuitive, but when something slides out a window, the timestamp is the time that it slid out, not the timestamp that was on it originally. Time is a big mess, by the way. Anyway, so it's a good question. Anything else before I show you the next feature? Yeah?
So if I had packets in one stream that haven't yet arrived and they arrive way late,
yeah,
then the estimate of the flags could be changed when new packets come in.
Correct. Yep. Yep. Okay, so the next thing I'm going to show you is our monitoring system. So now we've got this query that's running, and on each of these components of the plan, we can actually monitor certain aspects. So let's start with the join. I have a couple things I can monitor on the join. I right-clicked, by the way. I can monitor the CPU usage or the join selectivity, and I'm going to do the join selectivity. And it gave me a window size, by the way. It said, monitor the current selectivity of the join, so the average selectivity over the last time window. Okay, so we can see that the selectivity of the join is roughly around 0.2 to 0.3. Selectivity, by the way, means when I get a new tuple from either side, on average, how many tuples does it produce in the join? That's our definition of selectivity. So if I get a new S tuple, on average, I'm going to generate about 0.3 new tuples in the join result. Okay? So that's one thing I can monitor over time. I can also monitor on a queue the rate of tuple flow. So this is the S side, and let me just, so we can see here that the tuple flow on this queue is approximately 70, and in fact, if we look here, currently I have the slider set to 65 tuples a second. So what we can see is that all the data that's coming in at 65 tuples a second is going through the queue. We're not getting behind at all. Okay? Let's see. Let me, for example, slide this S slider way up. If I go way up here, we should see a huge jump here, obviously. What we also see is a jump in the join selectivity as a result. That's because the way I've set up the data, the S tuples generally join with more things than the R tuples. Okay? So by increasing S, I'm increasing the average join selectivity. Now, there's a bunch of other monitors that I can put on. I can look at CPU usage, for example, so I can see that this output operator is using some tiny fraction of the CPU. This is some store. This is some temporary storage. I can see how many pages I'm using for this temporary storage. I can monitor the cardinality, so this is actually a window. And you can see that the cardinality of this window is about 200. And if you remember the query, I actually had a 200-row window there, so that's looking pretty good. So now I've got all these monitors running. Now here comes the really cute part, which is how I've actually implemented these monitors. Let's look at our query. So we registered one query, remember? Whoa, where do all these come from? These are actually all SQL queries that are being used to generate those monitors. So in fact, what happens is when I put a monitor on one of those elements in the query plan, that element starts writing measurements off to a special stream called SysStream. You can see it right here. Okay? So we've predefined under the covers a single stream called SysStream. And a monitor says, I'm going to write, say, my throughput if I'm a queue, or I can write my cardinality if I'm one of those windows, onto the system stream. And then the monitor registers a SQL query over that stream. Okay? And then the results of that query, which, as I said, was a moving window average, are fed to the actual visual monitor. Okay? So we could look at a plan for one of these. This is a monitoring query. So down here it's looking at the SysStream and it's doing a selection to pick out the particular element that's being monitored, the particular measurement, and then it's doing an aggregation. Now here's something really cute. We can monitor the monitoring query. Okay? Why not, right? So now the monitoring query is writing something onto the SysStream, and now we've got a new query. And we can monitor the monitoring query of the monitoring query if we wish, and so on. Okay, so that's the monitoring system, and it's actually worked pretty well. I think it's pretty cute. Let me finally just show the benchmark. Actually, it's not that exciting except the complexity of the benchmark, I guess. Hello. This doesn't look good, does it? I doubt I lost my network connection. I think I probably actually just creamed the system. Let me see. Let me just do this quickly. Maybe I did lose. This seems unlikely. All right. Everybody talk among yourselves. Oh, fatal I/O exception. That looked pretty good. Now you know for sure this is a real demo. Okay, everybody talk among yourselves for a moment. Just launch this guy again. It's one of the first times I've actually had a public crash. But again, I'm not even the least bit embarrassed. But this does not look good at all. Maybe I crashed the whole machine. Interesting. What?
That was a web page not loading.
So you think we've lost the network connection?
No, problem with the web.
We'll try this one instead. Well, it looks we've lost something. Not sure what we've lost. Maybe we've just brought down all of Stanford's database group. Well, you know, I guess we're not going to be seeing the benchmark. The only interesting thing about the benchmark, to tell you the truth, was the complexity of the query plan. So all I do with the benchmark is I show it running, and I say it's generating these totals, and then I say, look at this, and you see this gigantic, huge mess of a query plan with cycles in it and things like that. So just take my word for it. OK, so that's it, and I'm happy to take more questions.
Any other questions?
Yeah.
So when you have multiple queries and you need to generate the execution plan, do you apply some technique in multi-query optimization?
Well, as I mentioned, right now the only thing we do automatically is share the streams and generate the maximum window. And we know we also have algorithms for doing it for a subclass of our query language. We don't have algorithms for doing it in interesting ways. Obviously, we could do a direct syntactic match, and if we had a syntactic match, we could glue them together. But that didn't seem even worth implementing. So, haven't done much yet.
Other questions?
Yeah.
So since the window construct in SQL returns the results that are not ordered within each result.
Yep, that's a great question.
So for typical stream applications, what if I want to say I want to put some constraint in, let's say, the second element, between the second and the first element?
Can't do it in our language, and that's one of, so there's a couple things that we should have done. One of them is this coarse grain sliding that I mentioned, and the other is what you've described right there. We don't expose that ordering, and we probably should have. Yep.
Part of the overhead of using any database system for such kind of stuff would be probably the concurrency control and the logging which goes with it, right?
Yeah, but you can turn off logging,
So
right?
I was wondering, like, how much of those functionalities do you have in such a stream-based system? Because
Those functionalities like logging?
Concurrency, logging.
No.
Because it seems that it's a simple case of concurrency at least. It's a read-only kind of scenario for every query. And every query is going to be a...
Yeah, we have no
very nice.
concurrency control because, well, so technically the relation updates need to be serialized and then generate timestamps at the end of the commit or something like that, which we're not doing. Right. So that portion of the system needs to have the usual stuff, but the stream is append-only, read-only. Yeah.
So I think it's related to that question that if, I were to ask you that, compared to relational database systems and the stream-based system, what do you point to as the unique technical part which makes that huge difference in order of magnitude? If you have to, give your bet on what's the secret sauce?
So the performance secret sauce or the expressiveness secret sauce? So I think the performance secret, well, one of them is just that you don't do all these inserts, So I haven't looked at the code that they wrote for using Oracle. If they make a, as I mentioned before, a JDBC call on every insert, then forget it. You're already completely out of luck. Doing everything in memory and guaranteeing it stays in memory is important. The scheduling algorithm is completely different. I don't know if there's a single. Yeah, that's not going to disk, obviously. It's a huge deal, right? And not making these heavy calls to connect to the database.
The one approach I would take in such a simplistic scenario is I would just, instead of using triggers, if I know that they are poorly implemented, I would just use a polling kind of an application. Because I know that the underlying thing would be a read-only scenario.
You're going to poll every second?
Every 30 seconds or whatever the benchmark says.
And run a query?
Every that.
And then cache the results of the query and do a diff?
That would be one approach, whichever is faster. Because that means you can alternate using relational system.
Well, yeah, you can certainly do it running a query periodically and running a diff on a query, but that diff can be very expensive. You're going to be caching the query results. I don't think that would be a very effective way of doing it.
My approach would be to use whichever is the faster mechanism as a fair comparison.
Oh, I see.
Because I'm using I'm reducing as much work of this extra pieces which we have in the system.
If you tried to run this benchmark with your style, it would you'd get like a 1,000th of an expressway. Because it's very dependent on fine-grained sliding windows and doing something at each slide. And if you try to run diffs over static states, that's absolutely not going to work. Right. I think the benchmark is very difficult to implement in many of the simple ways that you would think about because it's so based on history and sliding windows and such.
Can you access the timestamp from inside the language?
That you could not access the timestamp from inside the language, and that is, that would be one way of dealing with your question, but then you can say very complicated queries that are very difficult to optimize. But that would be one solution. It's something we debated. It's a good possibility. Yep.
Thank you very much.
You're welcome.